Okay, so in this video, we are going to prove some properties of matrix algebra when it comes to addition, subtraction, and multiplication of matrices. We will look at 3 examples. We will leave the other properties as exercises, and we will conclude the video with 2 exceptions. There are 2 exceptions when it comes to handling matrices algebraically with respect to addition, subtraction, and multiplication. And so the rule of thumb will be that when you handle algebraically matrices, you can handle them as if they were real numbers, except there are 2 things you have to watch for. And this will be the conclusion of our video. Let's start with a very simple example. Suppose we have 2 matrices of the same size. This will be number 1, our first proof. Suppose that both A and B are M by N matrices. And if you remember, you can only add 2 matrices of the same size because we are adding corresponding entries. So if you recall, Rmn is the set of all M by N matrices with real entries. So we'll prove that addition commutes, that A plus B equals B plus A. So first, if you remember, matrices are equal if they have the same size and the same corresponding entries. So let's see. If we do A plus B, A is an M by N, B is also an M by N, and since we are simply adding corresponding entries, if we add an M by N matrix to an M by N matrix, the result also is an M by N matrix. And the argument works, of course, in the other direction. If you compute B plus A, well, B is an M by N matrix, A is an M by N matrix, the result will be also an M by N matrix. So clearly, if you do A plus B or B plus A, you get a matrix of the same size. We will now prove that they have also the same corresponding entries. And we have to give a general proof. We have to prove that for any matrices A and B of the same size, that A plus B and B plus A not only have the same size, but also the same corresponding entries. So we take an arbitrary entry of A plus B, sorry. So we'll take the entry in, say, row I, column J. So for any row, any column. Well, if you remember, we are asking for the entry of the new matrix A plus B in the ith row, jth column. But when we add matrices, we simply add corresponding entries. And so we take the entry of A in that very same position, plus the entry of B in that same position. When we add matrices, we add their corresponding entries. But this is the entry of matrix A in row I, column J. This is a real number. This is the entry in matrix B in row I, column J. Those two are real numbers, and real numbers commute on their addition. And so we can reverse the sum. This is Bij plus Aij. Now we're simply done. If you add the entry in B in row I, column J to the entry in A in row I, column J, you have the entry of matrix B plus A in row I, column J. So you see, this proves that the entry in A plus B in the ith row, jth column is the same as the entry in B plus A in the ith row, jth column. This proves that matrix A plus B has the same corresponding entries as matrix B plus A. And as they have the same size, this proves that A plus B is equal to B plus A. And we're done. See, that wasn't so hard. Now, let's prove a property involving matrix multiplication. This is when things are a little more interesting. So you say, okay, well, we'll need here 3 matrices. So suppose that we take A and B to be of the same size. So A and B are M by N matrices. And we're going to want to multiply A plus B by a matrix. So the number of columns of our matrix will have to match the number of rows of A and B. So we'll take C to be a matrix, say a P by M matrix. We want to show the following property. that if we do C times A plus B, we can distribute the multiplication. This is simply C times A plus C times B. A well-known property of real numbers, which also is true of matrices. Well, again, to prove that matrices are equal, we have to prove that they have the same size and the same corresponding entries. Let's prove that they have the same size and then the same corresponding entries. So, the left-hand matrix, A plus B, well, as A and B are m by n matrices, the sum is also an m by n matrix. If we multiply by C, which we assume is a p by m matrix, well, as you can see, the number of columns of C equals the number of rows of A plus B, so multiplication is defined. The result will be a p by n matrix. So C times A plus B is a p by n matrix. Let's look at the right-hand side, CA plus CB. Well, C is a p by m, and both A and B are m by n. In both cases, multiplication is defined, and in both cases, CA is a p by n, CB is a p by n, and so the sum will also be a p by n matrix. So once again, it's very easy to check that C times A plus B and CA plus CB have the same size. Let us prove that they have also the same corresponding entries. This is where things are a little more interesting. So we have to consider an arbitrary entry of the left-hand matrix and show that it equals the same corresponding entry of the right-hand matrix. So our matrix is C times A plus B, and we consider an arbitrary entry, therefore an entry in row I, column J. As we have a multiplication, things are more interesting. If you remember, to find the entry in a product of matrices in the ith row jth column, we have to multiply the ith row of the first matrix, which is C, by the, or times, the jth column of the second matrix. And so, okay, so we take the entries in the ith row of C, the entries in the jth column of A plus B. So here be careful. Since we take the jth column of A plus B, that is our second index. And how do we multiply a row times a column? We multiply corresponding entries, so 1 with 1, 2 with 2, 3 with 3, so in general, k with k. And we proceed to add them up. All right, let's look at this term now. We have the summation over k, the entry in matrix C in the ith row kth column, times, if you look here, we take the entry in matrix A plus B in the kth row jth column. Well, as we've said before in a previous example, when we add matrices, we add corresponding entries. And so the entry in the kth row jth column of A plus B is the entry in matrix A in the kth row jth column, plus the entry in matrix B in the same position, kth row jth column. But these are just real numbers. This is the entry in C in the ith row jth column, entry in A and B in the kth row jth column. So we can distribute this product since we have real numbers. So we'll have CIK, AKJ, plus CIK, BKJ. Well, if we're summing all these terms, we can sum the terms in any order that we choose. So we can sum all of these and then sum all of these. So we can split up our summation into two summations. So let's sum first all of these terms together. So CIK, AKJ, and then we'll add all the leftover terms, Cik, Bkj. But here's where it's interesting. We can collapse our summations. Because if you look here, we are taking the entries in the ith row of matrix C, in the jth column of matrix A. We are multiplying the corresponding entries, and we are adding them up. This is by definition the entry in the matrix C times A in the ith row, jth column. And the same goes for our second sum. We can also collapse this one. We take the entries in the ith row of C, jth column of B, we again multiply corresponding entries, and we add them up. This is by definition the entry in matrix CB in the ith row, jth column. So now we get something that will look much simpler. This is the entry of matrix CA in the ith row, jth column, plus the entry of matrix CB in the ith row, jth column. But if you think of it, when we are adding corresponding entries, this would be the exact entry in the ith row, jth column of the matrix CA plus CB. If you're not sure about this direction, go backwards. If you're asking, how do I find the entry in the ith row, jth column of the sum of CA and CB? Well, we are simply adding corresponding entries. So the entry of CA in the ith row, jth column plus the entry of CB in the ith row, jth column. But this proves that the matrix C times A plus B and the matrix CA plus CB have the same corresponding entries. And so this proves that the matrix C times A plus B equals the matrix C times CA plus CB. And this completes our proof. As both matrices C times A plus B and CA plus CB have the same entries, the same corresponding entries, and the same size, they are therefore equal. And we're done. Now let's prove one last property. This will be our third and last example. And this is to prove that multiplication is associative. This one is really fun because it looks so trivial, but the proof is actually so interesting. So here's our third example. So here, we'll let A be an M by N matrix, B be an N by P matrix, and C be a P by Q matrix. We have three matrices. So here's what we want to show. We want to show that matrix multiplication is associative. So if we do A times BC, that is the same as doing A times B first, then times C. This looks so trivial, but it actually is quite subtle. So we'll prove this, and then I'll give you a simple example as to why this may look trivial, but is actually quite subtle. So again, to prove that this equality is true, we have to prove that both matrices have the same size and the same corresponding entries. Let's prove the same size first. So we have the matrix A times BC. Matrix B is an N by P. Matrix C is a P by Q. So the product is defined as P equals P, and the result of BC is an N by Q matrix. A is an M by N matrix. I'll write it here. And N equals N, therefore the product is defined, and the result of A times BC will be a M by Q matrix. So A times BC is a M by Q matrix. Let's look at the size of our right-hand matrix, AB times C. A is an M by N, B is an N by P, n equals n, multiplication is defined, and the result is a M by P matrix. C is a P by Q matrix. P equals P, multiplication is defined, and the result is a M by Q matrix. And as you can see, both A times BC and AB times C are M by Q matrices. So both have the same size. Let us prove now that they have also the same corresponding entries. And this will be quite interesting as we have not just one, but two multiplications taking place. There's the B times C and then times the A. And because there are two multiplications, we will end up with double summations. So we have to prove now that the two matrices have the same corresponding entries. So we take an arbitrary entry of our left-hand matrix, so A times BC, and so we take the entry in the ith row, jth column. As I and j are arbitrary indices, we have an arbitrary entry of the matrix A times BC. Well, once again, when we have a product, this is A times the matrix BC. If we want the entry of this product in the ith row, jth column, we take the ith row of A. We take the jth column of the second matrix, which is BC. We multiply corresponding entries, so 1 with 1, 2 with 2, in general k with k, and we add them up. That's our first summation, our first expansion. But here's our second multiplication between B and C. So we can once again expand. The summation over k of aik stays the same. And now once again here we will expand. We have the matrix B times the matrix C, and we want the single entry in row k, column j. And so we take the kth row of B, we take the jth column of C, and we multiply corresponding entries. So 1 with 1, 2 with 2, 3 with 3. Here be careful, we can't use k as our dummy variable, as we have previously used k as our dummy variable. So we need here another dummy variable. I'll abuse notation a little bit. I'll forget that we've used m for the size of a previously, and I will use m again here for our dummy variable. And once we multiply corresponding entries, we have to, of course, add them up. And you see we have two summations. What is our next step? Well, you see we are summing here with respect to m. So m is the index of summation, m is changing. If you look at the term here, aik, there is no m. So with respect to m, aik is a constant, and we can move, therefore, aik inside the summation, basic property of sigma notation. So sum with respect to k. After we've moved aik in front, we're going to have sum of k, sum of m. So we have a double summation of aik, bkm, cmj. And this will be probably a first for you now. We have a double summation of a product of three real numbers, a, b, and c, aik, bkm, cmj, but we know that we can sum real numbers in any way that we want. So here I will reverse the order of summation. Instead of summing first with respect to m, then with respect to k, I will sum first with respect to k, then with respect to m. And this is again legitimate because those are real entries. And we can add real numbers in any order that we see fit. So we have aik, bkm, cmj. What's interesting now is that with respect to k, Cmj is a constant, right? This term does not contain a k. Therefore, with respect to k, it is a constant, and we can move it out of the first summation, the summation with respect to k. So what will this look like? Well, we'll have the sum with respect to m. We're moving Cmj outside of the summation with respect to k, so Cmj. And we will be left with the sum with respect to k of aik bkm. And we can actually collapse now this summation. If you look at this, we are taking the entry in A in the ith row, the entries in B in the mth column, we are multiplying corresponding entries and adding them up. This is by definition the entry in the product matrix AB in the ith row, mth column. And so we're back down to a single summation. It is the summation of Cmj ABIM. But Cmj is a real number, ABIM is a real number, and so we can change the order of the product. We'll have the summation over m of AB IM Cmj. And once again, this should look familiar. We are taking the entries in the ith row of matrix AB and the jth column of matrix C. We are multiplying corresponding entries and once again adding them up. This is by definition the entry in matrix AB times matrix C found in the ith row jth column. But if you look back up, what have we proved? That the entry in the ith row jth column of A times BC is the same as the entry in the ith row jth column of AB times C. Therefore, not only do A times BC and AB times C have the same size, but they also have the same entries. The entry in the ith row jth column of A times BC is the same as the entry in the ith row jth column of AB times C. This proves that both matrices are equal, as they have the same size and the same corresponding entries. And so A times BC equals AB times C. This completes our proof. And you can appreciate from the proof why the result is actually not so obvious. On the surface, it looks so simple. But if you look at the machinery that we had to use to prove the result, then you get the feeling that maybe this is not so trivial. Now, to illustrate the complexity of the proof, and to give you a better appreciation as to why this is not entirely trivial, we'll consider a simple example of this property. So an example of number 3. That matrix multiplication is indeed associative. So we'll take the matrix A to be, say, a 2 by 3 matrix. We'll go 1, 2, 3, 1, negative 1, 1. We'll take matrix B to be a 3 by 2 matrix. Let's go with 1, negative 1, 2, 2, 0, 1. And we'll take C to be a 2 by 3 matrix again. We'll go with 0, 3, negative 1, 2, negative 1, 4. Let's compute the first matrix, so A times BC. So we'll do that first. So A times BC. Whoops. A times BC. Well, to compute A times BC, we must compute BC first. So we'll say, okay, this is A. So 1, 2, 3. 1, negative 1, 1. So A times BC. B, 1, 2, 0. Negative 1, 2, 1. Times C, the matrix 0, 3, negative 1. 2, negative 1, 4. So let's compute this. Two multiplications. We first perform B times C. Once we have this matrix, we'll then multiply it on the left by matrix A. Well, matrix B is A 3 by 2. Matrix C is A 2 by 3. 2 equals 2. The product is defined, and the result would be a 3 by 3 matrix. So A stays there for now. 1, 2, 3. 1, negative 1, 1. Times now our 3 by 3 matrix. Well, to construct this first row, we fix the first row of B and go through every column of C. 0 minus 2, negative 2. 1 plus 1, 3 plus 1, 4. Negative 1, negative 4, negative 5. To construct the second row of BC, we fix the second row of B. 0 plus 2, 2 times 2, 4. 6 minus 2, 4. Negative 2 plus 8, 6. And to construct the third row of BC, we fix the third row of B and go through every column of C. 0 plus 2, 2. 0 minus 1 minus 1. 0 plus 4, 4. Now that we have BC, we can compute A times BC. Well, let's see. A is a 2 by 3. BC is a 3 by 3. Multiplication is indeed defined, and the result will be a 2 by 3 matrix. So once again, to construct the first row of our new matrix, we fix the first row of A and go through every column of BC. So we'll have negative 2 plus 8, 6 plus 6, 12. Then we'll have 4 plus 8, 12 minus 3, 9. And finally, we'll have negative 5 plus 12, 7 plus 12, 19. To construct the second row, we fix the second row of A and go through every column of BC. So we'll get negative 2, negative 4, negative 6, plus 2, negative 4. 4 minus 4 is 0, plus negative 1, negative 1. Finally, negative 5, negative 6, negative 11, plus 4, negative 7. And so we now have matrix A times BC. Notice that in the product of matrix A times BC appeared a 3 by 3 matrix. Let us now compute AB first and then times C. Okay, so here's matrix A. So 1, 2, 3, 1, negative 1, 1. Times matrix B, which is right here. So 1, 2, 0, negative 1, 2, 1. So we first perform this multiplication between A and B, and then finally times C, which is right here. 0, 3, negative 1, 2, negative 1, 4. Okay. Let us perform the product, and hopefully our proof is correct, and we'll get the same 2 by 3 matrix at the end. Well, A is a 2 by 3 matrix. B is a 3 by 2 matrix. The multiplication is defined. The result will be a 2 by 2 matrix. And right away, this is interesting because when we did first B times C, what appeared was a 3 by 3 matrix. We never had, in the order of this multiplication, a 2 by 2 matrix. And you can see now, instead of the 3 by 3 matrix, we will get a smaller square matrix that will be a 2 by 2 matrix. So our calculations will be quite different. Let's see what comes out. A simple 2 by 2 matrix times the matrix C. Well, as always, to construct the first row of our new matrix, we fix the first row of A and go through all columns of B. We'll have 1 plus 4, 5 plus 0 gives us 5. Then we'll have negative 1 plus 4, 3 plus 3, 6. To construct the second row of our new matrix, we fix the second row of A and go through both columns of B. We'll have 1 minus 2, negative 1 plus 0, negative 1. Then we'll have negative 1, negative 2, negative 3 plus 1, negative 2. And again, it's worth looking up. This is what you obtained when you did A times BC first, a 2 by 3 matrix times a 3 by 3 matrix. And by doing AB first, what you have now is a 2 by 2 matrix times a 2 by 3. So you see in the first calculation, we never saw this matrix appeared, and vice versa. In our second calculation, we never saw this 3 by 3 matrix appear either. Drum roll, let's perform this multiplication and hope that we get the same matrix. This is a simple 2 by 2 matrix. This is a 2 by 3 matrix. Multiplication is defined. The result will be a 2 by 3. So far, it's looking good. The same size as before. A 2 by 3 matrix. So again, to construct the first row of our new matrix, we fix the first row of the first matrix and go through every column of the second matrix. So we'll have 0 plus 6 times 2, 12. Then we'll have 15 minus 6, 9. And we'll have negative 5 plus 24, 19. If you look up, same row as before. 12, 9, 19. 12, 9, 19. So far, so good. To construct our second row, we will fix the second row of the first matrix and go through every column of the second matrix. 0, negative 4, negative 4, negative 3 plus 2, negative 1, positive 1 minus 8, negative 7. And if we just look back up, indeed, our second row is negative 4, negative 1, 7, negative 4, negative 1, 7. So it does match. So you can at least now, hopefully, after the proof of associativity that A times BC equals AB times C, you can appreciate that this is not so trivial because the proof was not so trivial either. And by looking at a numerical example, you can see that the calculations are completely different. By doing BC first, we obtain a 3 by 3 matrix, then multiply this by a 2 by 3, and by doing AB first, we obtained a 2 by 2 matrix, then we multiplied a 2 by 3, and in both cases, even though we performed completely different calculations, we ended up with the same 2 by 3 matrix. So yes, we do have associativity, but it's not because it looks so trivial that it actually is. And now we'll conclude with the two exceptions. There are a lot of other properties that we could prove. I will leave them to you as exercises. The key to keep in mind is the following statement. When it comes to algebra and matrices, with respect to addition, subtraction, and multiplication, it behaves just like addition, subtraction, and multiplication of real numbers. Everything works the same, except there are two fundamental differences. Two properties that are true of real numbers no longer hold for matrices. And this will be the conclusion of our video. But always keep this in mind. This is the simplest way of thinking about it. When you handle matrices algebraically with respect to addition, subtraction, and multiplication, you can treat them as if they were real numbers, except you have to watch for two exceptions. Here they are, and I'll show you an example in each case. So the first exception, in general, even though both AB and BA may be defined, they are not necessarily equal. This property is true of real numbers. A times B equals B times A. No longer true in general of matrices. Clearly, if A equals B and B equals A, this is obvious because we'll have A times A is A squared, A times A is A squared, so clearly A squared equals A squared. But in general, if you take an arbitrary matrix A and an arbitrary matrix B, where the product is defined, AB and BA will not be the same. We'll give an example in a few seconds. The second property, which is usually true of real numbers but is not true of matrices. So if we have that A is not 0, so A is not the 0 matrix, so at least one of its entries is not 0, then if you have AB equals AC, if you think of real numbers, if A times B equals A times C, and the real number A is not the 0 real number, you can cancel A on both sides and prove that B is therefore equal to C. This no longer holds of matrices, so we lose our simple cancellation law of matrices. So even though AB equals AC, and A may not be the 0 matrix, we cannot conclude, it does not imply, that B is necessarily equal to matrix C. So the simple cancellation rule of real numbers is not true of matrices. We will later on fix this. We'll find a criteria, and we'll call this invertibility, whereas if A is invertible, we'll be able to cancel it, and once we cancel A on both sides, we will then conclude that B equals C. But in general, even though the matrix A may not be the 0 matrix, and AB equals AC, it does not imply that B equals C. Let's look at two very simple examples. But you always must keep those in mind. So an example for the first property. Let's take two very simple 2 by 2 matrices. Let's take A to be 1, 2, 3, 4, and B to be negative 3, 2, 5, 1. Let's compute AB and BA. As both A and B are 2 by 2, AB and BA will also be 2 by 2 matrices. Alright, so as always, we construct our first row. Fix the first row of A, go through the columns of B. We'll have negative 6 plus, negative 3, sorry, plus 10 is 7. Then we'll have 2 plus 2 is 4. Second row, negative 9 plus 20, 11. 6 plus 4, 10. And that is matrix AB. Let's compute matrix BA. Negative 3, 2, 5, 1, times 1, 2, 3, 4. Once again, the result is a 2 by 2. Let's construct our first row by fixing the first row of B and going through the columns of A. So we have negative 3 plus 6, positive 3. You see right away they're not going to be equal. Entry in the first row, first column of AB is 7. Entry in the first row, first column of BA is 3. So we could already stop there, but let's just complete the multiplication. Negative 6 plus 8, positive 2. Then 5 plus 3, positive 8. 10 plus 4, positive 14. So look how different AB and BA are from one another. So we can clearly see that AB is not equal to BA. And you can try and make up other examples on your own. Pick a random 2 by 2 matrix A random 2 by 2 matrix B, compute A, B, and BA, and almost always you will get different matrices. Let's look now at property 2. I should say lack of property 2, our second cautionary tale. So we need here a non-zero matrix for A. So I will take the matrix 1, 0, 1, 0. Sure, both of these are zero entries, but these are not. And so A is not the zero matrix, which we write as a larger 0. Because the zero matrix is the matrix where every single entry would be 0. This is not the case, so A is not the zero matrix. Let's take matrix B now to be 4, 5, 8, 9. And matrix C to be 4, 5, 1, 1. Clearly, B and C are not equal. They have the same row, but the same first row, I should say, but not the same second row. So B and C are not equal, but let us prove that AB and AC are actually equal. Let's compute AB. You'll have 4 plus 0, 5 plus 0, so it's going to be 4, 5. Then same thing, same row times the same two columns will give you the same row again. And therefore you have the matrix 4, 5, 4, 5. Let's compute AC. Well, 4 plus 0, 4. 5 plus 0, 4. 5 plus 0, 5. The second row is the same as the first row, which will give us the same second row. 4, 5, 4, 5. And you can clearly see that AB and AC are equal. But look at this. The two conditions are satisfied. A is not the zero matrix. Check. The matrix AB and the matrix AC are equal. Check. Can we conclude that B equals C? Clearly we can't, because we can see that B is not equal to C. And this disproves the simple cancellation law that holds for real numbers does not always hold for matrices. Even though A may not be the zero matrix, if AB equals AC, we cannot always conclude that B equals C. As I've said before though, we will very shortly find a criteria as to when we can cancel the matrix A, and this will be the idea of invertibility. But I want to conclude with this. The simplest way of thinking of matrix algebra when it comes to addition, subtraction, and multiplication is that it behaves just like real numbers, except that in general for matrices, AB is not equal to BA, and even though AB equals AC, where A is not the zero matrix, we cannot always imply that B is equal to C. So we can't always just cancel A if A is just not the zero matrix. And that's what you should keep in mind. So whenever you handle matrices algebraically, handle them as if you handled real numbers, always in the back of your head thinking of not doing one of these two operations. And that's it.